Okay, hi everybody. I think we're gonna get started. Welcome to the Great Lakes Seminar Series. I am Ayumi Fujisaki Manome. I will be kicking off this introduction. And thank you for your participation. I hope everybody online can hear us okay. If not, please type it in the chat so we can help address. I'd like to begin by thanking our host, which are NOAA's Great Lakes Environmental Research Laboratory, and also Cooperative Institute for Great Lakes Research, particularly Margaret Throckmorton and Aubrey Lashaway for hosting logistics, and also Guerrero IT team for making technology happen. So thank you so much. Today, we have a very distinguished speaker, Professor Christiane Jablonowski from the Department of Climate, Space Sciences, and Engineering at the University of Michigan. Prior to joining Michigan, Christiane also worked at the National Center for Atmospheric Research, or NCAR, and NOAA's Geophysical Fluid Dynamics Laboratory, or GFDL. She also has worked at the European Center for Medium Range Weather Forecast. Christiane's research lies at the intersection between weather and climate modeling, scientific computing, and data science. In particular, her research portfolio includes atmospheric fluid dynamics, weather and climate modeling, coupling techniques, climate model hierarchies, scientific computing, and machine learning techniques for climate sciences. She works with the weather and climate models from NCAR, NOAA, and Department of Energy. Professor Jablonowski is the recipient of the Department of Energy Early Career Award and the Presidential Early Career Award for Scientists and Engineers, or PCAS. Both of them are very prestigious awards. She is also a co-lead of the NOAA's convection-allowing model for short-range weather forecast with the Unified Forecast System. And she serves on the steering committee for NCAR's Community Earth System Model, or CESM, and a member of AMS Committee on Artificial Intelligence Applications to Environmental Science. Christiane has also been a close collaborator of the teams at Guerrero and Sigler on advancing Great Lakes weather modeling research. So without further ado, I'd like to pass it over to Christiane.
Thanks so much. It's a pleasure to be here, and I want to start with acknowledging all my collaborators, because a lot of the material you see today is actually produced by them, and I have the pleasure of presenting it to you. So I want to also, there are a few, of course, here in the audience from GLUL, also from Sigler. So I just want to maybe walk you through this list, and I see the mouse. So yeah, David Wright, I see him also here in the audience. He has also been working with me as a postdoc for some time at the University of Michigan. Ayumi, of course, Brian, Dan Titze here from GLUL, and Brian, I see you here, and yeah, Greg Mann from the National Weather Service, Pontiac office, Eric Anderson and Alexa Yeo. They are at the Colorado School of Mines, and maybe Eric, yes, you probably know he was here also for a while, and Ufuk is a collaborator of us from NCAR. And they're all crucial, and you will see pieces of them here fitting into the big picture. And I called this talk, yeah, representing lake atmosphere interactions in NOAA's, weather modeling world, or weather prediction models. And you will kind of see a portfolio of them. Hopefully, well, I made sure that I'm, defining all the acronyms. NOAA has a lot of these modeling acronyms. If not, stop me, and I'm explaining them. Also, if you have questions, feel free to interrupt at any time. All right, let me get started. So, well, why are we even interested? Okay, this is probably even a slide that most of you are familiar with. Why are we even interested in, exploring the intersection or the interactions between lake and atmosphere models? And of course, in the Great Lakes domain, it's a very pressing issue. I bet are familiar with lake effect snowstorms, and here's just a depiction I grabbed from a NOAA site even what it is, if you haven't seen it. So lake effect snowstorms are really specific here to the Great Lakes area, or in areas where not just the Great Lakes, but we need big bodies of water to produce them. But it really is here and this is something we experience quite a bit here in Michigan, if cold air comes from the north or, kind of northwesterly regime going over the lakes, and this is here kind of the long fetch, especially in those cold winter outbreaks, the lakes often not quite frozen yet. Yeah, so when you even think about November, December, evaporate like crazy if the cold air hits the lake, still warm from the fall. Not frozen yet, and that actually leads to cloud formation. The evaporation grows, cloud forms, and they snow like crazy once they hit the shore, and especially if there's a little bit of topography or orography along the shorelines, which is often the case, especially near Lake Superior up in the Northern Peninsula. So that's just one reason why it is beneficial or helpful to model lakes and atmospheric motions together and exchange information at the interface. There may be other reasons you can think about, and I listed just a few. This is not, a really complete list, but as we also here in Michigan are aware of just the presence of the Great Lakes, it's delaying actually seasonal onsets, fall and spring season onsets. We have, of course, this big regional moisture source that's providing additional, moisture into thunderstorm activity. And it's even from the literature, it's clear that just the presence of the lakes and the moisture is impacting the intensity of cyclones and anticyclones in various seasons. So that's there's a longer list here. It's even suggested that the Great Lakes, they impact even the low pressure systems over the state of New York. So, in even remote areas. So it's not actually just the regional impact, but also kind of really the bigger scale impact on the United States. Okay, so these are just reasons why we might be interested in that coupling idea between lakes and the atmosphere. All right. Okay, let me maybe hit home on that lake effect snowfall story. And this is, I bet many have seen this. This is just a satellite image of lake effect snow events here hitting actually hard. Here's Lake Michigan. We see Lake Superior here. Basically, all the lakes are impacted here, Lake Erie. And just by kind of looking at it, and I think I have actually, let me just go further. I have a little bit of a blow up. Here's Lake Superior. You see this really fine scale structure in the lake effect. And that's really something to acknowledge. Yeah, in order to even get the interaction right between lakes and the atmosphere, we might actually need to look at very fine scale models, meaning a few kilometer grid spacings in the atmosphere. Yeah, when you just think about those snow bands, they have, width maybe of a couple of kilometers, maybe 5, maybe 10, but in order even to capture this, even a 3-kilometer mesh in the atmosphere is kind of marginal. Yeah, so really ideally you want to be at 1 kilometer spacing when you think about the atmospheric motions and the cloud formation. So, well, the snow formation, there are even many ways lake effect snow can come about, and I have another example here for you in a minute. It's really this interaction is, it's really grounded, or when you look at the forcing mechanisms of the interaction, you go back to the lake surface and you look at sensible heat fluxes, latent heat fluxes. That's really what you need. Yeah, you need really good information. How do you get that? Well, you need good water temperature. You need knowledge about the ice condition. So if there's ice, there's even no evaporation. Yeah, this is a crucial component. So all those lower boundary conditions are the key to getting the interactions right. Okay. So here's even a neat example, and Brian gave that to me a while ago. So this is actually a very neat example of a lake effect. And again, they come in various forms and shapes, these lake effect snowstorm events. But here's a fascinating one, and this was happening last January, here just before AMS last year. And here's an event, lake effect event. This is now a radar image here. You kind of see Lake Michigan here, and you see even those embedded mesovortices here in this lake effect snow event. That was also captured. This is now kind of the radar image here, of course, but we also have actually from that event satellite observations. This comes from the SAR satellite, which I think even gets maybe correct me if I'm wrong, David, that gets administered here, here at Laurel. And that gives fascinating, this is wind speed actually, but this actually shows a fascinating image of this really sharp edge here in terms of the wind speed that's related here to that swirl. Yeah, so this is a mesovortex system. It was dumping a lot of snow here along the shorelines. Just a really neat kind of depiction of another lake effect snow event. Again, in order to capture this, we need very high resolution, atmospheric resolution, and we need really accurate information about latent heat fluxes, sensible heat fluxes, and lake temperatures. All right, let's kind of dive in. So what I want to show you are a couple of various, well, distinct points, let's say it this way. First, I want to just introduce you, if you haven't seen the acronyms, I want to just introduce you to the Unified Forecast System, or the UFS. This is the modeling system at NOAA, which is now used by the Weather Service. So this is something, the Unified Forecast System is led by EMC, NOAA EMC in College Park, and other agencies are participating in that. It's not just EMC, GSL, other NOAA agencies, and of course collaborators. So let me just briefly talk about that. I also want to talk briefly about the lake coupling and lake modeling capabilities that we have here at Laurel that we are utilizing in this project. And then let's dive in and look at a couple of examples of that lake atmosphere in action. This is mostly David Wright's work. And from there, we actually look at a couple of other items. For example, can lakes even be modeled with 1D versus 3D? Kind of just exploring a couple of options. And also looking ahead, how can we make the coupling even more sophisticated? And what I mean by that, how can we make it actually online, make it work online? What I will show you today is, let's maybe call it poor man's coupling. So it's actually not 100% fully coupled in an online fashion. It's like an offline coupling strategy. I run the lake model, FVCOM, I run the atmosphere model, I run the lake model, and so on, and they feed each other. That's working, but that probably will not be the future, and I want to convince you about that already. Okay. All right. So I was grabbing, this is now from a publication by Uche Lilly from BAMS a couple of years ago, and this was when this big vision was put together, that maybe even before then. So the vision of the Unified Forecast System started even before 2022. During that time in 2022, there was another effort by NOAA to put in a new activity or new center, which is called EPIC. EPIC is a center funded by NOAA that actually hosted at Raytheon, interestingly, but it's actually a center that really should help the innovation within NOAA, the innovation in the modeling world. Okay, and what this really conveys, and I called it, then and now, what NOAA had before, let's say 2018-19. So I know you can't read this, and that's also not necessary, but this is a laundry list of 21 distinct models in the NOAA modeling suite that took care of various aspects of the forecasting enterprise. For example, a wave model, we had a distinct local model, a distinct global model. Nothing overlapped. They were all complicated. They had their own workflows and so on. And back then it was realized that this should not continue this way, and we should go, and this is kind of here on my right side, we should go to a unified framework, let's call it this way. There are still models. It's not that this is just one gigantic model, but it's a framework that now reutilizes and reuses parts. And here's kind of the vision of the Unified Forecast System, that we have within this framework, that we have applications, and the applications could be very distinct. For example, seasonal forecasting, hurricane forecasting, short-range weather forecasting, or even global scale, of course, medium-range forecasting, or if you go down here, coastal processes are part of it. So it's actually not just one gigantic model. I don't view it as that, but it's a framework that lets you pick and choose. And it's kind of coordinated, put into a coupling framework. And let me just show you what I mean by that. Here are the components, the 8 components, the current 8 components of the Unified Forecast Framework. So you see still, standalone modeling components, of course, atmosphere, ocean, wave, land, what you expect. Also storm surge composition, this is air chemistry, or chemistry, yeah, for air quality, CICE models, and also there is a whole atmosphere effort, ionospheric forecast for like, solar events. So this is basically the framework, and there is a coupling layer in between. You don't see it here. I come back to it at the very end. That's called maybe as a heads up, Earth System Modeling Framework, ESMF. And that lets you pick and choose. And that's where the strengths come from. So if you want a coastal application, you actually might just want to pick the wave and the ocean model for a coastal application, maybe not even with an atmosphere on top, but maybe with a prescribed data atmosphere on top. You don't necessarily need maybe the full atmosphere interactive, but you may be just good with ocean and wave forced by a data atmosphere. And those pieces, whether this modeling piece that you're looking at is a full model or a data model, that's basically all provided. And that gives us the strength. It gives us this flexibility. So whenever, maybe let me just go back one more time. So whenever you pick something from this list of your applications, you pick from your portfolio, which is, in your modeling framework unified. That's the strength. And even some components, for example, the atmosphere, when you think about the atmosphere, you can maybe argue, well, yes, we have hurricane atmosphere, for hurricane forecasting or short-range weather or the global medium range. Even in the atmosphere, we share many of the same components, the fluid dynamics solver, for example. Yeah, so that's really the framework. You think about that as you pick and choose. It's glued together via a coupling interface, and it doesn't need to be fully online. It can also be a data interface, but it's all taken care of, and that's the strength of the UFS. Okay, and the other thing that is, of course, important for NOAA is just this, seamless coverage of timescales. And this is also from Uccelelli's, it's this paper, that this is kind of covering, the UFS would be covering, of course, all those different, when you think about it, from nowcasting hours of forecasting for maybe tornado events to days, short range weather, weeks, like 2 weeks, medium range weather, to maybe a couple of weeks in subseasonal, seasonal timescales, and maybe even down to or up to years. I want to highlight 2 things, and these are, let me just kind of get this here. So, and these are the only 2 things I have time for today, but I want to talk about days of forecasting and weeks of forecasting. Yeah, so I'm not actually in this range of long-term forecasting, I should say, yet. But today we focus just on kind of a couple of days, short range, high resolution, and medium range weather forecasting. And here are also acronyms you might encounter, medium range weather, short range weather. The tools are in the UFS are the Rapid Refresh Forecast System, and the other one is the so-called Global Forecast System, GFS. So the names are different, but they are indeed components of the UFS. Yeah, so it's not something new. Yeah, you pick from that portfolio and you put together your GFS, or you put together your Rapid Refresh Forecast System from the components. Okay, so let's take a look at, and this is not quite my last slide on the modeling, but and this is, I borrowed from Curtis Alexander. He's a scientist at GSL, and I thought this kind of, conveys kind of the essence of the day-long or days worth long forecast system. So this is now, really just giving you a little bit of information about the Rapid Refresh Forecast System, or RUFUS. Yeah, that's kind of the name. And one thing that's actually noteworthy is this huge domain. So kind of look maybe at the red outline here. This is kind of an extended, North American domain, including Alaska. And also note that there are other domains featured, and those are domains in blue that were captured by the old way of doing business. Yeah, so the old way, where we had 21 models, they were just responsible. For example, we had a model for this region, a model for the Konos region over the United States. We had even single models for Guam or Hawaii and those applications. Yeah, so this is now not the case. Yeah, so we have actually a pretty big box in red now capturing all the domains at once. Of course, at an expense. I don't want to hide that, at a computational expense. Maybe just a few words. 3 kilometer grid spacing. This is pretty fine resolution for today's standards. 65 levels, going up to about a couple of hectopascals, so 40 kilometers or so. And the rest, I don't want to read it to you, but there are just information about physics, some choices you make about microphysics, and whether you have additional aerosols, smoke and dust, and other things. Yeah. So this is this new forecast system is slated or supposed to replace HRRR, the current operational NOAA weather forecasting system in the future, and it could be next year. This is currently up for debate. Yeah, so this RRFS system has been in development. Well, if you think about it, for 9 years, so it's a long time. We might be at a stage where this is indeed good enough. Hopefully, we will see this year to become operational next year. And this is where we are heading. So when you think about my theme of interaction, lake atmosphere interaction, we interact with RRFS. Yeah. So I also want to say the current operational model, HRRR, is also interacting with lakes, and that was done, actually worked by Ayumi and colleagues. So we actually follow in their footsteps, and the next version of RRFS will actually do a lake coupling to GLER's model, which is FVCOM basically, and now operational, called GLOVES. Okay, I come back to that already. Okay, this is now a slide that I grabbed from Ayumi, actually. She presented that at AMS. And this is a slide that just kind of gives you now information about the lake coupling or the lake modeling capabilities here at GLER. Let's kind of take a quick look. You see the Great Lakes. So the operational model, which of course many of you probably even work on, the operational model here currently at NOAA is the Great Lakes Operational Forecast System, GLOVES, and that's based on FVCOM and has been developed over many years here within GLER. And what it is basically covering all 5 lakes here in the Great Lakes area, and it's looking, I don't know whether you see this, this is a pretty high level, very fine unstructured mesh here on top of the lake domain. Yeah, so this is actually the trick to getting really good coastlines, really unstructured meshes, very fine resolution down to maybe 200 meters or so, with a stretched mesh here in the open domain of a couple of kilometers. So that's kind of the principle of our lake model. It's FVCOM, or you call it here within GLER, you also call it Great Lakes Coastal Forecasting System. All right. Operational for 3 years now. And the way, and here's another view here of the mesh, here's another triangulation. The way we envision it, so here's kind of just close up what we want to do. So what's the basic idea? Basically, we want to take the lake conditions, meaning ice coverage, basically, lake temperature, and ice temperature. So just kind of the surface conditions, grab it from FVCOM and pipe it into RRFS. So this is kind of where the forecasts go. And these are pre-canned conditions. Pre-canned means we run FVCOM offline, forced with atmospheric data, but we do have that forecast of FVCOM for a few days already. And then we take that data file and we pipe it back into the next iteration of RRFS, or the next iteration of the forecast system. So this is kind of the idea. It's not online coupling. It's back to back. We run FVCOM, we run the atmosphere, we run FVCOM, and so forth. But they are pretty much in sync. Okay, that's kind of the basic idea. And as I just argued, we could do it over this big domain, but think about it. The Great Lakes are tiny in this big picture, so that would be a lot of compute. So in order to test this coupling, we actually don't want to do this in the big domain, but we just do it locally. And that's another feature that this modeling framework offers. You can also do, a smaller limited area configuration. This is now just kind of the Great Lakes area. Okay. We do need, of course, for those limited area models, you need some boundary conditions. As you run the model, you will need, temperature and wind, density, pressure here along the model boundaries. And we get that here from other models within the NOAA system, for example, the global model or another local model, which is RAP. So we are updating these boundary conditions here. And then we also, during the model run, we update or we prescribe these lake conditions coming from FVCOM, and that's a coupling step. So that's, and we do it, and this is on my next slide, we do it in various ways. Well, one way is, well, or as a control, let's say it this way, in order to know whether this is any good, whether the coupling actually gets you anything, let's also consider the control. The control is actually lake conditions come from someplace. Yeah, that could be coming from interpolated the host model GFS. These are pretty coarse resolutions. These host models, they could come from REP, but these lake surface conditions would be not up to date. Yeah, so they would actually be maybe informed by satellites at some point when satellites sees the lake, but they are not necessarily to the moment where we have cold air outbreaks. They are not capturing, they even might come from a climatology, which is even worse. Yeah, the climatology of lake ice, for example, sometimes even comes in as the lower boundary condition. I will show you it's not good. Yeah? What we then do, we consider static and dynamic updates. So control is state of the art. We just grab it from someplace. It's not really up to date. And static and dynamic means that we grab it from FVCOM, either just at step 0 at the initial time, or we update hourly. Yeah, so FVCOM evolves over time, so we would then update hourly. Okay, and let's pick a couple of case studies and see what we get. All right, and the case studies, this is a laundry list of a couple. I don't have time to really focus on all of them, although I show you a quick, preview of them. But I have a few more slides here on the November. These are lake effect snow cases. Yeah, so the November one is a more prominent one. That November one, let me also play this. This was also captured here by radar. This is now kind of the radar. Let me just play this one more time. So we see here actually cyclones, cyclonic activity even here for the lake effect snowstorm that then kind of hit here the upper part of Michigan, Lower Peninsula. All right. Okay, but here we see, and you see there are early season events like November and later season. And if you take a look, let's kind of go to the next slide. So this is now from David Wright's work, some paper we have in review right now, where those 4 case studies, which you see here, are evaluated. What you see here is actually lake surface temperature. I know it's small, and it's also not the point that we can read, all the points, but take a look, and I want to just kind of convince you when you look at, see my mouse here, control. This is basically lakes aren't really up to date. Static, we would use FVCOM at the initial time, and we can, and this is also the initial state for dynamic updates, of course. And here we have GLISI. This is the observational data set here at Laurel for lake temperatures. Down here, then we have comparisons between the dynamic change over a few days and also the GLISI change. What I want to just convince you that the control and GLISI, let's view GLISI as the truth. Yeah, so that may be not 100% correct, but that's an estimate based on observations. For some scenarios, we do see that the truth, for example, let me pick the January here, is pretty much biased, cold biased often here in the controls. So that's maybe an expectation. That's also true here for the November. Just kind of take a look at colors. The November case, I want to claim that we have, okay, maybe not here in Lake Michigan area, but that we have kind of better coverage here in, for example, Superior area in comparison to GLISI. Also true for, yeah, maybe not so much. Yeah, it depends. It's a mixed bag. But this is the overarching picture that we are seeing that often, not always. So FVCOM will have an advantage of getting kind of the distribution, this is temperature distribution kind of right in comparison to GLISI. The other thing I want to just point you to, and maybe we focus just on November case, GLISI, here's the change in GLISI, and here's a dynamic change in lake temperatures over a few forecast days. That actually looks alike. Yeah, we have actually pretty nice pattern over Lake Erie. meaning over that event, when the cold air came, we had significant cooling of the lake temperatures here in a couple of degrees. This is substantial, and we are only talking about a 2-day event, 2-day forecast, and we get cooling of a couple of degrees in Lake Erie. It's a major cooling event, and that has major implications, and that's my next slide, for also latent heat fluxes. And if you now, so this is basically the same depiction, now just grabbing a couple of forecast hours into the forecast, as we maybe just focus on one of them here, the November event. We clearly see that when we compare the dynamics, this is now a little bit different display here, dynamic versus static, meaning, how is the dynamic the dynamic latent heat flux, I should say, evolving versus the latent heat flux when you only use lake conditions at time step 0, the initial state. We clearly see a diminished latent heat flux here over Lake Erie, and that's 100% consistent with ice growth. Yeah? So here we see massive ice growth over a couple of days, and once ice hits, latent heat flux gets diminished, and that's actually depicted. So I think there's promise. Yeah, we have skill with the FVCOM coupling, especially in the dynamic scenario. Okay, again, let's take another look here at the November case study, because it was indeed a major event for the Great Lakes. Here you see some of the measurements of the snowfall events. This is here over Lake Michigan. This is over 30 inches in places. And then here in Buffalo or Lake Erie, we had 81 inches, almost record. Yeah, it's quite incredible for that 2-3 day event. Yeah, so let's see how the coupling interface worked and whether the lakes helped. Okay, so here again, lake temperatures, maybe the first thing to look at, lake temperatures, static, dynamic, and control. So we have this is FVCOM. This is kind of the initial condition of FVCOM. It's pretty close to Dlisi down here, although it's not quite true, I guess, for Lake Superior. So let's not view FVCOM as perfect. Yeah, so that's not true. And we have FVCOM. This is now dynamic ice. This is after a couple of days of forecast. So this is initial conditions, is a couple of days in. And here we have the control initial condition. And this is indeed for most of the lakes, not for Lake Superior, but control, the state of the art, which isn't updating on the fly. It's really not well pet or not well matched in, except Lake Superior maybe, but it's actually not a good match here for the other lakes. As you maybe see, dynamic, okay, as we look at FVCOM again, and this is the event I'm pointing out already, or I pointed out, we get the significant cooling here over Lake Erie, and that's depicted also in our FVCOM simulation dynamic, or FVCOM-driven simulation dynamic versus static. This is FVCOM, this is lake temperatures. So, okay, that's couple it in. And so let's look at the atmospheric answer to that. Okay, snow water equivalent is a measure of snowfall. If you kind of boil it down and see how much water basically came down. It's not snow height, but it's kind of an equivalent measure. And if you take a look at that event for FVCOM, this is with control, this is FVCOM static. Well, they do look alike. So we, kind of with the placement. So we do have kind of placements of these, high snow water equivalents. Here's kind of the difference between the two, the static minus the control. So we see different placements here in the bands, in the snow bands, compared to observations. The FVCOM, although it's slight, I should say, it's closer, or it's matching it a little better. Though, I should say, just from a placement perspective, we do have a little bit of an overestimation in both cases here in that band, in the snowfall amount. And that's also depicted, I should maybe point out, the maximum snowfall was 131 here. So this is snow water equivalent. So that's actually more than the observed. So let's maybe ask a question, okay, static, when we couple it statically, maybe that's not quite cutting it in terms of snowfall or snow water event. amount. So if we are doing it one more time and look at static versus dynamic, so yes, they do look alike. This is now coupling FVCOM hourly into the atmospheric model. They do look alike from the placement perspective, but it is indeed helpful to reduce an overestimation. This is basically in this block, it reduces the overestimation here of the snow water equivalent in comparison to SNODAS, the observation. So these are now pretty good matches here, the dynamic update and SNODAS. So let's maybe conclude at that stage there is skill. And that's also true. And one more, this is kind of my last slide, and then I kind of move on to some of the other topics. There is also skill when we again look at static, dynamic. So these are our coupled experiments. There's also skill in comparison to HRRR. HRRR is the current state of the art. And it's indeed, when you look at SNODAS observations, these coupling techniques do beat HRRR, although this is also coupled to the lakes, but this seems to be, with the next generation of weather forecasting model, a step in the right direction, actually, in terms of accuracy. Okay, so that's good news, yeah. But this is only 2 days or 3 days. Yeah? These are short forecasts. So we might want to ask the question, well, what happens if you are after 15 days or so? Can we also do that? We have explored that, and especially we have explored, and this is a new question for FVCOM, we have explored whether FVCOM even would be up for the task. FVCOM typically is run for 5 days, never really that long. And we asked the question for the first time, can FVCOM have skill, or is there skill when we run medium range weather for 16 days? And this is now work led by our collaborators from the Colorado School of Mines, so Alexa Yeo and Eric Anderson, where we explored basically an FVCOM standalone and driven with GFS, medium range weather data, and looked at ice and temperature distributions over like 16 days, over 16-day forecast horizons. And this is now actually a composite of like a winter season. So it's not just a single event. This is 8 16-day forecasts in April 2022. And what I want to draw your attention to, your eye to, is 2 things. So we have shading in some areas, especially here Lake Superior, where we are looking at the root mean square error of ice. And you see big deficiencies actually in FVCOM here, lots of ice built up where there shouldn't, too much ice. But I think the interesting part, and this is a logical explanation, the interesting part is why, and it's because the driver, in this case, GFS, the forecast system, is cold biased. And that makes perfect sense. If you see this here, the bias, the temperature bias, is denoted here in the red to blue color, and this is in the dots basically. These are now station data around the Great Lakes, and we compare basically the truth station data with GFS, the forecast data, and we'd see big -4 Kelvin. That's a big bias, cold bias, and no wonder if you drive FVCOM with cold biased atmospheric data, that's what you should expect. And it's not just this, it's also the fact that GFS is not guaranteed even to look at actual ice coverage. And I want to just get the word out. This is if GFS, these longer term applications actually use climatologies, and I just grabbed that here from the NOAA, from the Laurel side. You see a little bit, okay, this is for Lake Superior, but just as a kind of motivation why I say that. You see actually climatologies of ice coverage for Lake Superior here for many years. It was about, let's see, 50 years or so. We see this big spread of climatologies, and down here in blue, this would be the average ice. This is more or less a climatology. And now you can figure, so down here, maybe just as a note, this was the ice last year. There was basically no, very little. But this, if you grab a climatology for ice, no wonder in GFS, no wonder that you can't just use that to drive or to interact with FVCOM. So FVCOM, and this is a statement for FVCOM, FVCOM will do a better, of course, represent a better coverage of ice distributions, more like the actual ice in each year. Right. Okay, but maybe one more yeah, I guess, statement about skill for, FVCOM skill for 16 days, not just looking at air temperature, which is this is what you just looked at, but also cloud cover. Now you see actually positive bias in cloud cover and negative bias in wind speed. And again, this kind of goes together. Yeah. So if we have cloud cover shielding, depends of course where the cloud sits, but if cloud cover shields the lakes, if we have positive bias, we also prevent radiation from going down to the lakes, which then enforces the cold bias. And also we have low wind bias, meaning we have not efficient enough mixing and advection of warm air. So this is all in the picture. Yeah. So we basically claim, yes, FVCOM has skill, but also we need to pay attention to the quality of the driver. Okay. Okay. I want to maybe go, and there's one more theme I want to hit on, and I should watch the time. Also, there are many other things I could show you. This is all from a publication here by Alexa Yeo, but we basically learn for these various lakes, Erie, Huron, Michigan, Ontario, and so on, that when you kind of focus a little bit, this is 16-day horizon forecast time, Root-mean square error, and we actually see that green and red are mostly better than blue, and blue means, well, you wouldn't, this is persistent. This would mean a persistence forecast. So you only give it, kind of the climatology basically, and you keep it constant, or you give it the actual, or you mimic actual like atmosphere interactions with two different products from the GFS here in green and blue, and you definitely, most of the time, I guess, you beat the persistence forecast. So there's skill. This is kind of the take-home message. Okay. All right. I want to wrap up a couple of minutes just with a couple of comments on smaller lakes. And this is new work that we engaged with over the last half a year or so, where we asked the question, well, the Great Lakes are good, yes, but what about smaller lakes? And I'm not talking about super tiny lakes, but like Red Lake, Nipigon, St. Clair, and ask the question, do we need FVCOM, or is like a 1D lake modeling approach, doesn't a vertical good enough? Yeah, those approaches are also out there for smaller lakes, just 1D in the vertical. Okay, and let's kind of take a little bit of a look. So basically we are looking now at a comparison of 1D, we call it CLM, versus FVCOM configured for those smaller lakes. And let's take a look at Lake St. Clair. Here's now a timeline over a year of CLM, 1D, FVCOM, and LISI. Like this is temperature data, and this is actually a pretty good match, yeah, as you see it now as a averaged on the on the Lake St. Clair basin. But well, if you look at RMSE in comparison to observations, we are not perfect by no means, but both are not perfect. CLM, but biased in different ways. I also want to note, here's a picture of bathymetry, and note this is a very shallow lake, and that matters. Yeah, I think that there's a hint that actually the deepness, and note we have the chipping channel here in Lake St. Clair, so it's a really deep 10-meter channel over a 3-meter base. That matters, yeah, for like creating those biases. But let's take a look at other lakes. So for Lake St. Clair, we are actually really good, and that's also true here for Lake Okeechobee. So when you kind of compare the timeline, here is a snapshot. The green line shows you again kind of temperature distributions, not a bias, but temperature distributions. And yes, it is kind of looking a little bit. The shading does look different. If you average over the basin, the overarching timeline is good. Also, we look here at shallow and simple bathymetry. We do have, and this may be obvious, it's good overall, but we do have that issue in CLM that we overheat actually coastlines. Okay, different biases, and now Red Lake, not so good. Yeah, so here we see a different lake, still relatively shallow. Here's now kind of the bathymetry, but here we are, and this is in CLM down here, FVCOM temperature distribution. You see both are biased here in the timeline over the kind of this time frame, but in different ways. Both are not good necessarily. Observations here speckled in satellite observations speckled here in black. So basically, they both have issues here in the springtime period, which is this initial period, overestimating and underestimating. You really see it actually here in this snapshot in May, the over and underestimation of the lake conditions, the temperature, and last but not least, Lake Nipigon. This is super complicated bathymetry, and also we see big, depending on season, but big deficiencies actually in both CLM and FVCOM to mimic the the spring and the fall distribution here of the lake temperature. Again, here's a snapshot in October, and you see these different biases. In this case, CLM is actually a little bit better in comparison to satellite images. So this is kind of an exploratory phase here for us to see whether FVCOM is also a viable tool for small lakes or small layer lakes. Okay, I want to close, and I'll give it 2 more minutes, with a couple of, I guess, technical steps, and that will prepare us for the future. And let me maybe skip to that. What I mean by that, we are doing poor man's coupling. Yeah, we are giving it a data file. It's not, it's pre-processed. We need to interpolate upfront from FVCOM to UFS. It's very brittle, yeah. And what this, for the future, what we want to do, we want to remove that point of failure potentially. And the way this goes is to now go to the so-called Earth System Modeling System or the infrastructure. This is a depiction, kind of a high-level depiction, what it means, and it has a coupling interface. And it has components. These are ocean, ice, and so components, the atmospheric components. But what it really means, this is a coupling interface, and it also can couple what I mentioned to the data model that's called CDEPS. So we don't need the active land or the active atmosphere. We can also couple to data. And that's the strength, and that's how we envision it. And I know this looks awkward, yeah, for maybe if you haven't seen software engineering diagrams, but what we want to do, and this is kind of maybe an easier look here. We want to give, and this is a data lake, for example. It can be online in the future, but we want to give it a data lake, go through the official coupling channels, and the coupling channels will do meshing, interpolation in time, interpolation in space, everything you don't want to do up front, they will be doing on the fly, and then feed it into the UFS, or even into the ocean model, or whatever you want to couple. And you can even maybe in the future then stream Michigan, Superior, Ontario as individual data lakes or online lakes into this coupling framework, which sits right in the middle. And really, if you want to know what it is here you see the domain, you see the Great Lakes. So when we run, this is the atmospheric component, we need the information about the lakes. We go to our coupling interface, we call the data lake interface. That CDEPS interface know what to do. It's grabbing the output. It's grabbing the input. This is FVCOM input. We see FVCOM input. Okay, it's high resolution. This is 25 kilometers. So now this whole infrastructure does the interpolation. I kind of noted here the spatial interpolation, the temporal interpolation. We do it on the fly, and that then feeds back. This is kind of now feeding back the interpolated values. And this is, you don't touch it. Yeah, it's just provided to you. You just give it a netcdf file input on FVCOM grid. You don't care about resolution of the atmospheric component. You don't care about time steps. You just give it and it works. So that's kind of where we are heading, and that will also be the place where you can do online coupling, not just data coupling, but online coupling. And maybe let me wrap up here. Okay, well, this was a walkthrough, pretty quick, I think. I told you something about the UFS and the modeling world here at NOAA, including the FVCOM modeling world. Where we are currently at a stage where we include FVCOM lake conditions into the NOAA forecasting system, especially as short-range weather application. We tested static and dynamic updates, both work, but we think the dynamic is the way to go, which is also good for long-term predictions, not just 2 days. So it will be a must-do, I think, the dynamic like hourly updates. We see that FVCOM has skill for longer time periods than 5 days. We think FVCOM has skill for small lakes, not perfect. But this is a promising approach to then let's us going to the next step, which is let's get rid of the poor man's coupling, although poor man's coupling will go into operations next year. Yeah. So we do have that on the book, but that is a logical next step that we then go to sophisticated coupling using, coupling infrastructure that the UFS wants, that's already in place, called ESMF. And that also will be the place to go for the next version of Rufus that will then entertain the ESMF coupling and prepare us for true online coupling, interactive coupling. Basically, run the lakes, run the model at the same time, let them interact at their own time scales, like you would do with ocean, land, and other components. All right. Okay, I want to close with also, acknowledging that this is NOAA funded work. Yeah, so these are the grants that funded our work. And of course, many people here in the audience are involved. And of course, I hope we have an opportunity also to continue this work as we go into the next, 3 to 5 years or so. All right, thanks very much.
Can you go back to the 1D simulation?
Yeah.
Okay, here. So you can see here is for the small lake, I can see the FVCOM have early warming.
Yeah.
And compared to the blue line. And how about the other lake? Could you go back to other
Early
lake?
warning, yeah. Let's go here.
Yeah, this one.
So this is Nipigon.
Yeah, so this one, FVCOM early warning and delay warming. So you run the model only one year, or you run the model for several years to see?
This is about a year of simulation. So you see my timeline day of year. This runs from January through December of that year.
So no initialization. So it's just around 1 year. So we know the FVCOM, I think this is the default scheme, right? So the numeric scheme in this version is unstable, have a warm bias in spring and fall.
Okay, that is not always the case. So I guess if I can maybe convince you, here we are seeing it actually in sync mostly.
Mm-hmm.
And also here for Langston Clear. So I'm not certain that's a whole story. I think it's also the bathymetry in the mix, the complete, maybe even the shape of the lake. It's very exploratory. So this was done last fall. So I'm not certain we have the full answer here.
Okay.
Yeah, you're right. It's intriguing to see. There are various biases, but they're different depending on the lake. And I bet we can see more if we go to.
Right. Okay.
Yeah.
Okay. Thank you.
Any other questions? James.
Thanks for the really nice talk. There's so much in this talk. It's a lot to digest. Very specific questions, I guess. But you showed at one point near the beginning, like LECE versus FVCOM and the dynamic change, sort of.
Yeah.
I was just curious. LECE is how its algorithms improved a lot, but it's impacted by cloud cover. So
I know. That's a good point.
So I'm just curious, were you able to see a seasonal dependence on that difference? It'd be really hard to see that when there's clouds, because when there's big dynamic changes in temperature, air temperature, or water temperature.
I don't know whether we know the truth then. LECE is probably the best bet. But thanks for pointing out. Yeah, LECE is actually a mixed product. It has satellite observations when available, but sometimes with cloud cover, satellites can't see the Great Lakes to see the temperatures. And that means that in some LECE products, if we have a cloud period, LECE observations might be 10, even more than 10 days out of date, and are still part of the observation. And that, of course, 10 days, I just convinced you that 2 days could do a lot to change lake temperatures. I do appreciate that comment. I'm not certain I have a better product to offer. Maybe
yeah,
you
certainly,
might.
Yeah. I was just curious if you looked at the seasonal difference or not. So thanks.
Didn't know. No. Yeah.
And then the second thing, also fairly specific, you showed the UFS biases If you can you go back to that if it's relatively easy? I was just sort of surprised. It seemed like the over lake biases were way less in the very few locations where you had a lighthouse or something.
Are you referring to which slide though?
I think you were just there, maybe. No.
This one?
The one with all the dots that are showing station validation of UFS.
Oh, yes, this one. This
Or,
one.
yeah. So I was just surprised. It seemed like some of the lighthouses are surprisingly unbiased, and it just seems, I don't doubt that it's biased over lake,
right.
but I'm just,
You're right. There is something to consider. These are stations near the lakeshore, but you're right. They are not necessarily on the water. But that's probably the best we can do, as maybe, kind of comparing. Well, this is near lake temperatures, but let's assume we don't really have measurements here over the lakes. In that, there's no buoy in winter here. We can't have measurements here, unfortunately. But we do believe, if there are all these cold biases, that of course the inner domain, the Lake Superior, must be biased in the same fashion.
Yeah, certainly. Yeah, I don't doubt it. I guess my comment was more just like pointing out that the biases vary drastically in space, I guess, which is just that's sort of surprising that UFS does that.
Also note, I didn't mention it, there's a very strong, you probably saw it, north-south bias. Yeah, so actually we are looking okay. Yeah, down here in, if you kind of look at the white means nothing or almost white. Yeah, so we have actually pretty good temperatures in the GFS. Driving temperatures for the FVCOM simulations here in Lake Michigan or over Lake Michigan near Lake Erie, but there is this inherent north-south bias actually in the driver, in the GFS driver.
Interesting.
Yeah, it's very, I find it excessive actually, I must say. But I think it's a known quantity that GFS is cold biased. So it's actually also, it's a task, of course, for the UFS, for the atmospheric team to even tackle those biases for forecast purposes, not just for FVCOM purposes.
Any more questions online? Yeah.
Can you go to the root mean square time series, 16 days?
Yeah.
Yes. This one, root mean square, this up to, this are ice, right? These are ice or? This is a prediction for ice or for?
No, this is temperature. That actually.
So.
Oh, I think you're right. It's ice. Ice coverage.
For Lake Erie,
it's ice.
Superior look okay.
Yeah.
And the Michigan okay. But Erie and Huron, particularly Erie, shoot up over 35%.
Yeah.
In 60 days.
Erie is very hard, as you probably know. Erie in FVCOM, I don't know whether some of you are involved in that, is over icing quite a bit.
It's over icing because New Mexico scheme have over icing.
I think Ayumi knows the
in
best
winter
story,
time.
but it is actually the shallow. When you think about the deep or the bathymetry, it's the shallowest lake of all the 5, and that leads to, for example, currently we have 100%, if I believe, maybe no longer, ice on Lake Erie, but not 100% on other lakes that are deep. So Erie in FVCOM has a tendency to over ice. This has actually happened even in recent forecast periods like this year and last year, and that's in FVCOM. So basically FVCOM is overestimating the ice buildup, and I think that's probably one of the deficiencies.
Surprising to me is the Superior is so good here, but compared to a root mean square in air temperature or SHT, surface lake temperature for the previous figures, that Lake Superior have the largest root mean square error. Not this one.
Okay. So which lake are you pointing to?
The map you just showed.
Okay.
Map.
This one?
Yeah, this one. So Lake Erie and Lake Superior have the largest. But for ice, it's.
For ice, yes, you're right. You're
okay. Right. Is something cancellation happened there?
Okay. I think this is well, Ayumi should be in a better position to comment, but there is this deficiency in ice modeling and air sea in action over Lake Erie.
I think in the interest of time, we should carry on this discussion to the afternoon.
Okay.
But thank you again. Let's thank the speaker again. Thank you, Christiane.
Thank you.